Hello guys and welcome. This is TATHYARAJ BHATTI. I hope you are all doing fine in this quarantine and pandemic situation. So today as part of my assessment I am going to give a small video presentation on nanophysics. So hearing the word nanophysics, the first question that comes to our mind is what does nano mean? Nano actually stands for a Greek word which means dwarf or small. So the unit 1 nanometer is equal to 10 raised to minus 9 of a meter or 10 raised to minus 3 of a micrometer. So to understand how small a nanometer is, consider a human being which is 6 foot tall. A 6 foot tall human being is 1.62 meters in height, which converts to 2 billion nanometers. That small is how a nanometer is. So, to get a better idea of how small a nanometer is, let's take a few examples. Suppose consider my hair. So, a hair is actually 80,000 nanometers thick in diameter. Or you may consider, suppose, my blood in my blood veins. So the red blood cells in the blood are actually 7,000 nanometers in diameter. So you may wonder which objects are around 10 nanometers or somewhere around that. So generally atoms are around 1 nanometer in diameter, or they can even be lesser than 1 nanometer. So whenever we think about the word nanotechnology, we always think it as something in the present or something more futuristic. But actually nanotechnology has been present on the earth for more than 2000 years ago. Like sulfide nanoparticles were used by Greeks and Romans to dye hair. They are of the nano size. Or you may consider in the Middle Ages, which is around 1000 years ago. Yes, 1000 years ago. They used gold nanoparticles to stain glass. So you may think if nanotechnology is present as far as 2000 years ago, so what's its use now? But the fact is that nanotechnology will drive the next growth cycle. It is estimated to become a $1 trillion market by the year 2020. It has many thousands of applications in mechanical engineering, aerospace, environmental remediation, pharmaceuticals and drug delivery, biotechnology, electronics, photonics, information storage, and many, many more. The co founder of Intel, Gordon Moore, gave us the Moore's law, which focuses on device miniaturization. He quoted, "The number of transistors incorporated in a chip will approximately double in every 24 months or in a 2 years of time." Moore's law, as it is called, drives the industry today. Here is a graph which shows how approximate is the Moore's law. On the x-axis we can see the date of the introduction, the years, and on the y-axis we see the number of transistors per square inch. It's just increasing as the years pass by. So before going ahead, I would like to introduce you to some nano definitions. So first is cluster. What is a cluster? A cluster is a collection of units, which may be atoms or reactive molecules, of up to 50 units. It is called a cluster. The second one is colloids. So what are colloids? A stable liquid phase containing particles in the 1 to 1000 nanometer range. are considered as colloids. The third one is the nanoparticle. So a solid particle which ranges from 1 to 100 nanometers in size. It could be non-crystalline or an aggregate of crystallites or a single crystallite. They are all considered into nanoparticle. And the last and the fourth one is nanocrystal. A solid particle that is a single crystal in the nanometer range is called nanocrystal. So as we go on, we may come across this question that why do we want to go into the nanoscale? So consider this example. Consider two identical cups with similar tea in the cups. So in the first cup we put sugar cubes, and in the second cup we put refined sugar. So we see that refined sugar will dissolve quickly and with more ease compared to the sugar cubes. And the reason for this is that the refined sugar has high surface area to volume ratio. So more the surface area, more the reactivity, as we all know. So as we go to the nanoscale, we attain very high surface area to volume ratio, which increases the reactivity of the reaction. The time is taken is also very less. So as we go down to the nanoscale, we see some effects like realization of miniaturized devices and systems while providing more functionality. That means that devices will get smaller, and at the same time they will be more functional. Like first there used to be the old telephones which could only be used to make telephone calls, but now we have these smartphones. So now it can do many things. We can play games, we can call anyone, we can be on the social media, all in this one small devices. In the similar way, nanoscale effects shows. So the second thing is that attainment of high surface area to volume ratio. We already discussed that. And some novel phenomena and properties will also be seen, like melting point will change, reactivity will change, conductivity, strength, and optical properties will change. Like I want to say here that you may wonder why optical properties might change. So please consider that nanoparticles are of the order of 1 to 100 nanometers in the nanoscale, and the visible range of light starts from 450 nanometers. So of course it will have a drastic effect on the optical properties of an object. Like I would like to give some examples, like we can see in the graph here. As we increase the particle radius of the gold, the melting point changes drastically. We can see in this graph. Or like when we decrease the crystal size, we can see this color change which occurs. So what are the advantages of nanotechnology? So the first advantage we'll see is in the material. So with nanotechnology we can create unique materials and products which are more stronger, of course lighter at the same time, also cheaper and durable, and very precise. The second advantage will come in the industrial sector. Computer will become a billion times faster and a million times smaller. Also we could tackle the pollution problem very easily and efficiently. And of course manufacturing will happen at very low cost. The third major advantage of nanotechnology will come in the medical sector. Like the illnesses like heart disease and cancer could be just wiped out, and also we could attain universal immunity like AIDS, flu, and also this coronavirus also. And also we could do body sculpting, that's like changing our appearance. So here we will see how nanoscale drastically changes the mechanical properties. We here usually see unique mechanical properties. And why does this happen? Because on the nanoscale we reduce the grain size, the materials become lighter, and their mechanical properties are enhanced. The main reason of this is due to the reduced imperfection in the materials. We can create tougher and harder cutting tools, like cutting tools made of nanomaterials such as tungsten carbide, tantalum carbide, and titanium carbide are very much harder, much more wear resistant, erosion resistant, and will last very long than their conventional counterparts. Also, they can be used in microelectronic circuits. The industry now needs micro drills with enhanced edge retention and far better wear resistance. These nanocrystalline carbides provides all these properties. They are stronger, they're harder, they're more wear resistant, and they are currently being used in micro drills. Another practical take on the nanotechnology is in the automobile sector. So we all know that as nanomaterials are stronger, they are much more harder, they are much more wear resistant and erosion resistant. They can be used in spark plugs. Why spark plugs? Because we all know that spark plugs are used in internal combustion engines, and how a bad spark plug can affect a vehicle. The fuel efficiency may decrease, the power output may decrease, also emissions may be more. So this can all be solved by nanotechnology. Also, automobiles waste significant amounts of energy by losing the thermal energy generated by the engine. Thus, if the engine cylinders are coated with nanocrystalline materials like zirconia or and alumina, which retain heat much more efficiently, which will result in complete and efficient combustion of the fuel. So we'll get more power in better fuel efficiency and less emissions. Nanotechnology will also be useful in aerospace components. The fatigue strength a material can hold increases drastically when we reduce the grain size of the material. Nanomaterials provide such significant reduction in the grain size over the conventional materials that we use, aluminum, iron, in the bulk form, that the fatigue life is increased by an average of 200 to 300%. This can drastically improve our performance in the space. Also, in spacecraft, the elevated temperature strength of the material is crucial. That at high temperature also, it should be very strong, because components like rocket engines, thruster, and the nozzles operate at much higher temperatures, much more in the radiation in space. So they all have to be tough materials. This all is possible with nanotechnology. As we go down to the nanoscale, the optical properties change. The optical properties of nanomaterials depend on the following parameters, like size, shape, surface characteristics, and their interaction with the surrounding environment. The optical property is significantly affected by decrease in size of the materials. It is mainly due to the two reasons. The first reason is quantum confinement of electrons inside the nanostructure. And second one is the surface plasmon resonance. Applications based on the optical properties of nanomaterials can be seen in lasers, photodetectors, sensors, solar cells, photocatalysis, biomedicines, etc. Now let's have a look on the electrical properties. Electrical resistivity of a nanomaterial increases. The resistivity increases once the dimensions go below the bulk electronic mean free path. Also, electrical conductivity of a properly oriented nanotube is extremely high, with the observation that carriers can pass through micrometer lengths. Now you may wonder, micrometer is not so much, but compared to nanometers, micrometers is 10 raised to 3 times more, like 1000 times more. So carriers can pass through micrometer length of available tubes with zero scattering and zero heat dissipation, like compared to no energy loss. Nanotubes frequently appear to be perfectly periodic over their lengths, but the only source of electronic scattering is the thermal vibration of atoms. Last but not the least, the magnetic properties. So, surface atoms of nanomaterials can be modified by interaction with other chemical species by using some reagents. That is by capping the nanoparticles. Non-ferromagnetic bulk materials will exhibit ferromagnetic behavior after capping its corresponding nanoparticles with suitable reagents. For example, surface and core of aurum or gold nanoparticles with 2 nanometer in diameter will show ferromagnetic and paramagnetic character respectively. Means gold will show ferromagnetic characteristics in spite bulk gold being diamagnetic in nature. Also, surprisingly, very surprising, that permanent magnetism has been observed up to room temperature for thiol cap gold nanoparticles. Permanent magnetism has been observed in gold particles. So, thank you guys. This has been my time giving this video presentation, small video presentation on nanophysics. My name is TATHYARAJ Bhatti and hope you have a nice day. Goodbye.